So last time I just introduced the notion of linearly reductive groups. So if you have an affine algebraic group G, it's linearly reductive if there exists a G invariant linear map from the coordinate ring of G to the base field and we normalize it such that R of 1 is equal to 1. And so I call this the Reynolds operator, and in fact, we can show if it exists, it's unique. And this notion of linearly reductive is equivalent, turns out, to that every representation is a direct sum of irreducible representations. And anyway, so many ways of defining linearly reductive. So in general, linearly reductive are reductive in the group theoretical sense, but the converse is not always true. Last time we saw, for example, that a finite group is linearly reductive when the characteristic of the field does not divide the group order. And in fact, that's if and only if. In characteristic 0, all the classical group like GLN, SLN, symplectic group, and so forth, they're all linearly reductive. But in positive characteristic, those groups are not linearly reductive. For example, if we work over the complex numbers, then we can describe this Reynolds operator as follows. If I have some function on GLN, then I can take the average, but I cannot really integrate over a non-compact group. I just choose a maximal compact subgroup, the unitary group. And so I just integrate over this maximal compact subgroup. And I normalize, this is a Haar measure. And normalizes Haar measures such that UN has volume 1. So then this would be such a Reynolds operator, would satisfy this property. It's invariant under the unitary group automatically because it's a Haar measure. But since this actually lies the risky dense in here, it's actually automatically also GLN invariant. Now, if we don't work with the complex numbers, but some other field of characteristic 0, then we have to have a different description. And we want, for computations, we want to have some kind of algebraic description of this Reynolds operator. So, so if you work over a GLN of an arbitrary field K, so then there's another way using this so-called this Cayley operator. So remember that the coordinate ring of GLN is described by this kind of polynomial ring, and then we localize with respect to the determinant of this n by n matrix. And so if you have some element in here, or no, now let's say, first of all, I define this differential operator as follows. So we take this matrix, should be Z, this matrix of partial derivatives. And now I take the determinant of that matrix. That's a differential operator. That act on, for example, this coordinate ring. Now, if f is, say, homogeneous polynomials in the z variables of degree d, then, first of all, sorry. First of all, let me define, so we can apply this omega to the power k to the determinant of z to the power k. So this differential operator decreases the degree by n. And so you see that if I apply this, this will be a constant. And so this will be some constant, which you can actually show is actually a positive constant. And so, so now we can define this Reynolds operator. It turns out to be as follows. If I take a f and divide it by the determinant of z to the power k, then the Reynolds operator applied to this is equal to omega to the power k f divided by this constant ck. If this degree d of, f is homogeneous of degree d, if d is equal to k times n, and 0 otherwise. So that's sort of an explicit algebraic way to define this. So for algorithms, we need to be able to compute this Reynolds operator explicitly. All right.
So in this first definition of the Reynolds operator using a unitary group, when you write down this formula for a function f, is it like a priori you define it only for functions that take values in the unitary group and then you can extend, or?
So f is a function on GLN.
Yes.
But I let's see. Yeah, but I guess I just take the average over the unitary group.
Yeah. Okay.
But the values over the unitary group completely determine the whole function. Okay. So the group G acts on its own coordinate ring. It also acts on this dual space. So this dual space is quite an interesting object because it contains everything. First of all, right, if we can embed G into this vector space by, G, we can send it to G, what I call G star, which is just a function that's evaluation at G. Now, of course, also the Reynolds operator itself lies in this dual space. It's a map from OG to K. And also the Lie algebra of G also lies in that. So to see that, right, we have a map from the coordinate ring. Let ME be the maximal ideal corresponding to the identity. Then we have a map from the coordinate ring to ME mod ME square, given by F goes to F minus FE. So that lies in the maximal ideal. Okay. And so then if we dualize, then we have an embedding. So this is surjective. Then we have a map from the dual space to the dual space here. And this is just a tangent space of the group at identity, which is the Lie algebra of G. And so this Lie algebra also lies in this dual space. And in fact, we have this multiplication, and the dual to this multiplication is this co-multiplication. And then we can dualize again And basically, we all write like this. This gives us a multiplication on this dual space. So this space is actually an associative algebra, right? Which is an associative algebra that contains this Lie algebra. So it also contains the universal enveloping algebra. Well, it actually contains the universal enveloping algebra of G. So it's a really nice picture. And the thing is, if you have a, suppose now we have some representation of G. So suppose the gamma, so this is how I defined earlier, you know, a rational action. If we have any element in this dual, the way it acts on V is, so we can evaluate at some, sorry, we can apply this A and here gamma. So then we get a map here, which we can think of as an action of this algebra. So this V is an OG dual module. So this all at once also defines an action of the Lie algebra on V, in particular also an action of the Reynolds operator. Okay, so I define RV going from V to V by RV of a vector V is just R, try to write curly, R applied to V. Right? Just how this R acts on this vector space. So let me, first of all, so what can show using all the axioms, which, you know, we can show, for example, that the image, so the image turns out to be exactly the space of invariant vectors. So we have, so all the properties, right? So more precisely, this here is a projection. Also, if we have, if this is a G equivariant linear map, then we have this commuting diagram. Okay, so this diagram commutes. So in particular, so this is phi, and this is the restriction of phi. In particular, phi sends invariance to invariance. If you look at phi of V, if you look at the invariants that lie in the image, this is RW phi of V, and because it's commute, this is phi of RV V, which is just phi of the space of invariance. In particular, if phi is surjective, then WG is the image of VG. One interesting case is if X is an affine variety, if X is a fine G variety, well then in that case, G acts rationally on the coordinate ring of X. So then we also have a Reynolds operator, or the action of a Reynolds operator, that goes from OX to the invariant ring. Again, this is a projection it goes onto. And so this is actually also a way to find lots of invariants, right? Because basically you just take an element here and you can project and get invariants. In principle, you can get all invariants that way. And this has also the property, this is an OXG module homomorphism. Not just a linear map, but actually a module homomorphism. Yeah. And the kernel is exactly the direct sum of all irreducible representations that are not trivial. Okay, so now let me talk about an algorithm for generating invariants. This is the algorithm that I actually appeared in my thesis, which is basically reduces the problem to computing a Gröbner basis. But first, let's look at the sort of general case. So first of all, we can do reduce the general case to the case of a representation using this Reynolds operator. So again, if X is an affine G variety, then we've seen that we have this G equivariant closed immersion. Where V is, say, an n-dimensional representation, n-dimensional rational representation. And from this we see that this on the level of algebras, we have a surjective K-algebra homomorphism. So this G equivariant surjective K-algebra homomorphism. And as I mentioned before, that kind of means that if you look at the invariants, right, this is the same as, in this case, the invariance here. So that means that if we have generators, so if OVG is generated by F1 up to FR, then the invariant ring for X is just generated by, we just apply this algebra homomorphism to these generators. So we can basically reduce the problem of finding generators for this algebra to the problem of finding generators for this algebra. Okay, so we reduce to the case of a representation. Let's look at the case of a representation. So let me just call this A for short. This is a polynomial ring in n variables, and this is a graded ring. This AD is the space of polynomials of degree D. We have this maximal homogeneous ideal so which is everything in degree, positive degree. And then let I be the ideal generated by all the invariants in M. Okay, so this is the ideal generated by all homogeneous invariants of positive degree. Okay, and so this appeared in Hilbert's proof of its finiteness theorem, right? So basically, Hilbert proved in 1819 that the invariant ring for linearly reductive groups is always finally generated. Well, you didn't have the term linearly reductive, but basically it applied to wherever, you can take, you can average of the group, or. And so basically what he proved is, let's see. Well, first of all, he said, there exists F1, F2, up to Fr in MG with, let's say, homogeneous. The ideal is generated by F1 up to Fr. This is just basically saying that this ideal is finally generated, which Hilbert proved in this paper. So we kind of needed to prove this final generation of ideals to prove this result in invariant theory. And then once you have that, then there's an induction proof that shows that these ideal generators, which are assumed to be invariant, they actually also generate the invariant ring. And that's a relatively easy induction proof where one also needs the Reynolds operator. Okay. But now, what if you have generators what if we don't have invariant generators? What can we say then? So here's the following lemma. If I... So first of all, maybe we should point out, this proof is not very constructive, right? It's not an algorithm at all, right? Because it just says, well, here's an ideal, and it's finally generated, but it doesn't say, how to find these generators, right? In fact, the proof was criticized by people like Gordon, who had already some algorithms for like SL2 that were very explicit, but this doesn't give any algorithm at all. But we can make this proof more constructive as follows. So if I is generated by some elements, let's say these Fi's are homogeneous, but I no longer require them to be invariant, well then one can show then this I is also generated by, if you just apply the Reynolds operator. So I'm just going to write R instead of like R OV in notation. This is just how this Reynolds operator acts. And so now these are invariant, and so then by Hilbert's result, we have generators of the invariant ring. So the question is now, find generators of this ideal I. Now to do that, well, we have to look at the following, let's look at the following map. G times V goes to V times V. It's sometimes called the graph of the action. It's defined by phi GV is V GV. And let B be the image of this map. Right? This image may not be, variety. It may not be closed. It's like a constructible set a priori. It's actually the equivalence relation, right? The image, but now let B be the vanishing ideal of B, which is also the vanishing ideal of its closure, which could be strictly larger. And so this is an ideal in OV cross V, which is like a polynomial ring in 2n variables. And note that we can compute generators of this ideal B using Buchberger's algorithm. Because it's the image of a morphism between affine varieties. So yesterday I explained how we can compute the image of a morphism between affine varieties. You use some like pure lexicographic ordering. You have to embed this, you have to view this G as some affine variety, so embed it into some vector space, and then and it's given by equation. And this morphism, you have to know like how G acts on this vector space. It's also given by some polynomials. Anyway, you can write out some ideal and compute some Gröbner basis and eliminate some variables, and then you get this ideal. And then I proved in my thesis that suppose maybe I should also point out this ideal I is far from a radical ideal. It turns out that the zero set is something very nice. It's actually the null cone, or the set of all unstable points.
Sorry, but if R is the Regnus operator, wouldn't R of F1 be like a scalar?
Yeah. Yes.
Then the ideal cannot be.
Oh yeah. Okay. I hear this R is actually this ROX.
OV.
So if you like, maybe like R acting on. So if you have this Reynolds operator, right?
Yeah.
That lies in OG dual space.
Yeah.
But this Reynolds operator acts on, if you have any representation, this Reynolds operator acts on it, right? And this action I denote by RV.
Okay.
And so it's really this action. Or instead of, sorry for being confusing, but this R that I wrote here really is this ROV. It's the projection of the polynomial ring onto the invariant ring. Right? And so if you have a finite group, then RV is basically averaging over the group. Okay, suppose this ideal is generated by some polynomials, H1, I use S in my notes. And let's say these polynomials are homogeneous. Well then, this ideal I is generated by H1 x0 up to Hs x0. So you only have to set the y variables equal to 0. So once you have this Gröbner basis of this ideal, then, or any generators of this ideal, then it's immediately you get generators of this ideal I, and then you just apply the Reynolds operator to these generators, and then you get generating invariants. So really the only real computation is finding this, finding the generators of this ideal, which is a Gribner basis computation. Yeah, so that's basically the whole algorithm. Okay. So that's sort of the general case for linearly reductive groups. Now let's look at what can we say about arbitrary reductive groups. First of all, let's say G is reductive. Okay. We also know that the invariant ring is still finally generated. Right, by a result of Nagata. And well, you also need the notion of reductive is the same as geometrically reductive, which is due to Harbush, at least one direction, the hard direction. Or more generally, right, if X is any affine variety, affine G variety, then the invariant ring is finally generated. And so we have this sort of categorical quotient. And this quotient has these nice geometric properties, right? So if X and Y are an X, then you cannot expect that this map is geometric, right? That this quotient is geometric in general. It may not separate all the orbits, but it can separate exactly when when the orbit closure of X and the orbit closure of Y. Sorry. So if the orbit closure of X and orbit closure of Y intersect, then it's not hard to see that pi of X has to be equal to pi of Y by continuity. And if the intersection is empty, if the orbit closures are disjoint, then this pi will actually separate these orbits. So let V again be an n-dimensional rational representation. So in the situation before, so we again have this ideal I. And so what is the zero set of this ideal I? So this Hilbert null cone, which we can define, for example, as we write pi inverse of pi of 0, sort of the zero fiber of this morphism, this quotient map. And this is exactly all the, if you think about it, is exactly the zero set of this ideal, right? So this ideal, let's see. No, I don't see it. This ideal, let's see. Oh, yeah. Where did I? Oh, yeah, here. So we defined I as this ideal generated by all invariants. This ideal MG corresponds to pi of 0, and then this I is an ideal whose zero set is the inverse image of this. And also, if you look at this property here, you see that this is the set of all V and V, such that the orbit closure of V intersects with the orbit closure of 0, which is another way of saying that 0 lies in the orbit closure. Right? And so this is a so-called Hilbert's null cone. And so these are exactly like all unstable points, right? So the semi-stable points would be everything else. Okay. But anyway, this null cone was studied also by Hilbert in this 1893 paper. So Hilbert actually gave another proof of finite generation. And the second one was a bit more constructive, although it's not really an algorithm by our standards. But
sorry, can I ask?
Yes.
When you say the semi-stable points,
Yeah.
do you mean for the action of G on the projectivization of the vector space, or?
Yes. So you could let G act on, P of V, and then you would here kind of take P of V as S inside, and that would be sort of the P V S S, I guess. Yeah. So some things Hilbert proved is okay. Suppose we have P1, P2 up to PR, which are invariants, let's say homogeneous. And suppose the zero set of these polynomials, or the ideal generated by these polynomials, is the null cone. And let P be the ring generated by P1 up to PR. Then Hilbert, one of the things Hilbert proved in his 1893 paper is that this invariant ring here is finitely generated P module. I guess technically maybe you only proved it in a linearly reductive case, but I think it easily generalizes once you know these geometric properties of reductive groups. And Hilbert used this fact to give another proof of finite generation. He also introduced, Hilbert's Nullstellensatz and other very fundamental things in algebraic geometry in that paper. Okay. It's actually particularly nice if the group is linearly reductive. So let me just say one more thing about linearly reductive groups, namely the Hochster-Roberts theorem states that if G is linearly reductive, then the invariant ring is Cohen-Macaulay. So this is a nice properties of modules or rings, which I'm not going to explain, but there's an important consequence to that. Namely, it means the following, that if P1, P2 up to PR are algebraically independent, then the invariant ring is a free P module. And still finally generated, right? So then, so in that case, it means that we have a decomposition like this, right? Where these Hj are some homogeneous invariants. And P is the polynomial ring generated by some homogeneous invariants. So I have the particular nice structure of the invariant ring. And the structure has also been used in various algorithms, maybe I'll get back to that at some other point, but for example, if you would be able to compute the Hilbert series of this invariant ring a priori, then, well, it's easy to compute the Hilbert series of P, and then you would kind of easily figure out what the degrees of these HJs are. So you could already predict in which degrees you would have to find these module generators. Anyway. And in this situation, sometimes these the P1 up to PR, if they're algebraically independent, are called primary invariants, and these HJs, these module generators, would be called secondary invariants. Although I should point out there's some choice involved. So these P1 up to PR, there's actually what can actually show there always exists such a algebraically independent invariance with this property using Noether normalization lemma. But this choice is not unique. And so okay. But let's go back to the reductive case again. Let's know. And we already can understand the linearly reductive case, so let's look particularly at the, assume the field is positive characteristic. Because in characteristic 0, linearly reductive and reductive is the same. And so actually, positive characteristic is most of the time it's worse, right? But there are also things that you can do in characteristic P that you cannot do in characteristic 0, right? Like, for example, taking the pth power is algebra homomorphism. In fact, the proof, this Hochschild-Roberts theorem, which is mainly a theorem in characteristic 0, actually goes through characteristic P, using tight closure of ideals and things like that. But anyway. If A, let's say we have two finely generated K algebras, just need some definition here, then maybe like the pth root of A is the set of all f in B such that f to the power P lies in A. Let's say K is algebraically closed. I think for some statements I at least would need perfect field or something. And A hat is the set of all f in B for which there exists an n such that fp to the power n lies in A. So we call this the inseparable closure. And so we actually have some algorithms to compute the pth root or inseparable closure. Now, to compute the inseparable closure, you basically just repeatedly take the pth root until it stabilizes. So we have an algorithm for that, but don't have time to go into that. But we can use this to compute generators of the invariant ring. Okay, so suppose so we again can look at the same map that I defined over there. Just using the same notations. So remember we had this B, which was the image. And I also want to look at the set S, which is the set of all VW in V cross V, such that pi of V is equal to pi of W. Set theoretically, this is sort of this, so this pi, remember this pi is the quotient map. So this B is an equivalence relation. This S is also an equivalence relation. Now, interestingly, if you take the closure of B, that's not an equivalence relation. So equivalence relation is not preserved if you take the closure. Kind of a strange thing. So one useful notion is this notion of separating invariants. So we say that invariants are separating invariants. I mean, you can also define this for an action of arbitrary if the zero set of fx minus f1y, etc., frx minus fry, if the zero set of that is equal to the set S. So that means that these invariants can separate orbits exactly when all invariants can separate them. Or well, when these FRs can separate orbits exactly when this quotient map can separate them. And so in that situation, so we basically have the following result, that if F1 up to FR are homogeneous separating invariants, then the invariant ring is the inseparable closure of A, where A is this algebra generated by F1 up to Fr. Okay. So basically, this is an algorithm due to Kemper. And later we sort of also generalized this to arbitrary affine G varieties. So the algorithm would be something like that, this roughly, like we can compute invariance degree by degree. And at each step, we can check whether we have separating invariants. Okay, so basically, what does that mean? This zero set has to be the same as the zero set. So we have kind of two ideals: the ideal generated by these elements, and the ideal that defines this. Oh yeah. So sorry. I have to explain how to find an ideal that defines S. So how do we find S?
Here, this inseparable closure is taken in the fraction field? Or
Sorry?
Where is this inseparable closure taken? I mean, it was defined when it is...
Inside the polynomial ring. Yeah. So this is our B. So as I mentioned, this S is an equivalence relation, B is equivalence relation, but the closure of B is not an equivalence relation. But we can take the transitive closure of B closure, and in fact we only have to do one step. So this S is basically, let me call this, let's see, what did I do in my notes? Oops. Yeah, define V cross V, this map here, which is the projection on the first and third coordinates, right? So say UVW goes to UW. Then S is equal to delta applied to, you take the closure of B times, wait, I think I wrote it wrong in my notes, but and then you intersect this. Okay, so basically this can be computed using Gröbner basis. So you have an ideal. You have ideal generators for the vanishing ideal of B. You do that in the X and Y variables. And then you take the same ideal in the Y and Z variables. And then you throw everything together. That will define, at least the zero set of that will be this intersection. And then you have to do some elimination to get an ideal that defines the set S. That may not be a radical ideal, but certainly you can find equations for the set S using Gröbner basis computation. So then we have some equations that define S, and we have some equations that define, and then we have these generators. And then you have to check whether the radicals of these two ideals are the same, but you don't actually compute the radical ideals. There's some better way of doing it, because there's an easy, well, not easy algorithm, but you can always check whether some polynomial lies in the radical of another ideal without actually computing the radical ideal. It's just like one Gröbner basis computation. So anyway, so then the algorithm becomes just computing generators degree by degree, and at each step checking whether the zero set is equal to S. And once it is equal, then you compute this inseparable closure. Okay, so it's an algorithm. It's probably not going to be very fast. And the thing is, with all this, it's kind of the more specific example you have, the more techniques you could use. So, like an algorithm that worked for general reductive groups is probably not going to be fast, but if you have a specific situation, maybe a finite group or something, then there may be other methods that can speed up. Okay. So the next thing I want to talk about are basically looking at some more specific examples. Yes, Evelyn?
So, do a separating invariant obviously contain some primary invariants? I mean, is there a relationship between these two things?
Yeah, I think if you have separating invariants, in particular, they would have to define the null cone. And then, well, you may have to take some linear combination of powers of these things to find the separating invariant, find the primary invariance. So, so if you have if you have separating invariants, and let's say they're homogeneous, they have this property that they will define the null cone, right? But they probably will not be algebraically independent. And so there's a way of making them algebraic independent if they're all of the same degree. Then you can just take generic linear combinations and take the right number of them, and then that will work. If you don't have the same degree, then kind of the only thing you can do is kind of take powers of them so that they all have the same degree, and then take linear combinations. And usually that would blow up the degree. Although in practice it usually is not really necessary to go to high degree, but theoretically one might have to. Yeah.
But that would be to just test that they are algebraically independent.
Well, there are some algorithms that will try to find first primary invariance. And then, yes, you would compute invariance degree by degree and make sure that, that these invariants are algebraically independent, okay? Which yeah, you know, involves some more Grübner-based computations. Yeah. Okay, finite groups. Yeah, probably won't. There's not too much time left, but I start with some. Let's start with at least a simple example that probably most people are familiar with already. You know, Sn acts on n-dimensional affine space by permutations, right? By permuting coordinates. Right, so the coordinate ring is a polynomial ring in n variables, right? And if you have a permutation, it acts on xi by sending it to x sigma of I. So then we have the elementary symmetric polynomials that are invariant. So the kth elementary symmetric polynomial is given by ik less equal than n, xi1, xi2 up to xik. So for example, E2 is say x1, x2 plus x1, x3 and so on, plus xn minus 1, xn. And then it's well known. And here k is really arbitrary, for now at least. And the invariant ring is actually generated by E1, E2 up to En. Okay. You can actually to see this, like suppose we have some invariant, right? Then I claim, certainly these are invariant, but I claim every invariant can be expressed in E1 up to En. So how would you do that? Well, if we have some invariant, then we can look at the leading monomial of F. And again, we use some monomial ordering. I'm going to use the pure lexicographic ordering again, as before. And you can look at the leading monomial of F. So this is some monomial, you know, x2 alpha 2, xn alpha n. But because it's invariant and I can permute the variables, you see that the largest monomial has to be of the form where alpha 1 greater equal than alpha 2 up to alpha n. So that means that f is some coefficient times x to the power alpha plus smaller terms. But now, using these invariants here, I can make a similar polynomial that has the same leading term. Namely, so in particular, if we take, say, h to be f minus c alpha times e1 to the power alpha 1 minus alpha 2, e2 to the power alpha 2 minus alpha 3, and so forth, en minus 1 to the power alpha n minus 1 minus alpha n, en to the power alpha n, then you see that the leading monomial of h is strictly smaller than the leading monomial of f. Now this pure lexicographic ordering is also a total ordering, it's also well ordering. And so by induction, you can say express H in E1 up to En. We can assume that, but if we can do that for H, then we can also express F in terms of E1 up to En. So that would be kind of the proof. But I mean, this is also an algorithm, right? Oh, looks like I'm out of time, so I'll stop here.
Any questions?
Yes.
So when you were talking about the separating invariants,
Yes.
do we have that a set of them will always exist? And if so, can we compute them explicitly?
Yes. So even if the ring is not finally generated, a set of separating invariants always exists. So that's a good point. So in our situation I was talking about, we were talking about reductive groups. We already know that the invariant ring is finally generated. But even if we had an arbitrary affine algebraic group, because right, this is about just because this is more a question about the topological space, which is affine space or X, not the quotient. So since that's Noetherian, right? So at some point, yeah.
Thank you.
You have a question?
Yeah, I think I lost track a little bit at some point. So you say that with the primary invariant, your module, your ring of invariant is free of a...
Yeah, if the group is linearly reductive.
And that works for... So it's not preserved for finite groups.
Well, if the finite group is linearly reductive, right? If the characteristic doesn't divide the group order, then it would apply. So.
And it applies for also bigger groups than finite.
Yes, whenever the group is linearly reductive. Yes.
So I'm curious about how do you implement this with the computer in practice. So for example, if you have like a semi-simple group and it's given by some combinatorial data,
Yeah.
a linking diagram, and then I give you some set of like integral dominant weights with some multiplicity. So that's the data of a representation, and I guess this is something you can put in a computer.
Yeah, you would.
Can you like then like this? Yeah, have an algorithm that computes the ring of invariants from this data, and you can like actually program it.
Yeah, so you would have to kind of express everything in terms of fine algebras and polynomials. So, like if you have the highest weight, you can have to actually really write down explicitly like the representation in terms of functions in the coordinate ring and so forth. But I mean, you could do that, but yeah.
So you could do this, but it would be maybe a bit pointless to do it.
Well, it has been done in the simplest case of SL2.
Yeah.
Reducible representation. When your highest weight is just a one active integer, and this is already quite tough.
It's quite tough to.
Yes. To
Yeah.
implement this has been done by Cohen. Algorithm to computing for binary forms.
So
The
it's
smallest,
it's tough to implement it, or it's tough to run it?
It is implemented.
Yeah, so exactly. So,
That's the smallest case, okay?
yeah, it's in practice it's quite limited the number of examples you can compute. So, for example, for finite groups things work pretty well. For SL2 you can do some things, but if you have bigger, examples, then you run into you get too many variables. If the number of variables increases, Gröbner bases become very slow generally. So that's why whenever you have more information, you can try to, there's definitely room for improvement and other methods that, for example, exploit more the representation theory. For SL2, already people in the 19th century already had pretty good algorithms for computing the SL2 case, which exploits more the representation theory of SL2, which is pretty simple. Yeah.
There's a question at the back, and then that one, and then maybe I'll go to Ivedan, and we can ask after because they cannot.
So this general algorithm, how expensive is this in terms of the dimension of the group and the dimension of the representation? Like if you have a general reductive, like a reductive group and some representation.
Yeah, so generally there are no guarantees, because just computing, the general bounds for computing a Gröbner basis is already doubly exponential in the number of variables, I think. So.
Double exponential, you said?
Yeah.
So in the case of looking at graded unipotent quotients, where there are these results which say that even for these groups being non-reductive, you still have finite generation of invariants. Are there similar algorithms along these lines that actually allow you to compute these invariants?
Can you repeat? You said in which case you...
So in the case of looking at graded unipotent quotients, so what Josh was explaining this morning, are there similar algorithms that actually allow you to compute these invariants in practice?
I don't know about that case in particular, but people have definitely looked at, for example, just like the simplest case, like for the additive group, like the simplest non-reductive case. And definitely we have algorithms for that, but that's also the case. In some cases, you can reduce computation of invariance of a non-reductive group to a reductive group using like the Gross-Hans principle. So, if for example, if you have a unipotent group action, for example, but the action extends to a reductive group containing it, and also the U invariance of the coordinate ring of this reductive group is finally generated, then this invariant ring is finally generated. Okay. Anyway, so there's some cases one can do it, and in particular also for the additive group, there's some ways, some algorithms.
Thank you.
Thanks. Are there questions in Ibadan?
Yeah, I think we have one here. Yeah.
My question is in section 4. So where you talk about categorical quotient. Yeah. So now the pullback of every point, you know that is contained exactly one closed orbit. Yes. Is it always true that all the orbits in S are precisely closed?
Sorry, all the orbits in
X.
Oh, no, in general, orbits in X, not all orbits have to be closed here, no. So what I've said applies to a general situation where not all orbits are closed. And of course, if you are in a case where X is a representation, then orbits are typically, anyway, orbits don't have to be closed.
Thank you. The second question is this. So now the last example you gave about symmetric group. Yeah. Yes. So if you pick alternating group now, so the group of even permutation, and we talk about AN invariant. Yeah. So SN invariant is containing AN invariant. Yes. Right. Mm-hmm. Good. Can we describe? How can one describe the Hobby space or AN invariant?
I will do that next time. So we'll just leave it. Yeah.
Any more questions, Josh?
I don't think so.
Okay. It's pretty time. I'm very mindful that we restart in 20 minutes, but I also know that you wanted to ask again. No?
The question now?
Yeah.
Yeah. Okay.
You don't have to.
Yeah, you can ask privately.
Yeah. Okay. Okay. Thanks.